So here we are with section 8.5. We are going to do integration by partial fraction decomposition. So that's a mouthful. And I want to, as usual, start out with stuff you already know how to do so that you can see old methods and why we need something more. That if your integral looks a little bit different, then that will hopefully kind of change your brain to switch over. So as usual, we're going to run through the stuff that we know how to do already and remind you of some of the basic skills along the way. So again, you can do 1 through 4 on this page on your own, pause the video, work on it, and then just sort of fly through and check your work. So let's get started with problem number 1. Again, you don't need anything fancy for problem number 1, although you do need the first integration technique that you learned, which is your basic U substitution. So normally we use a U substitution for something inside a composite function, but this is one of those times where I'm going to let U be the entire denominator. I'm going to let U equal x squared plus 4. And once I decide to do that, of course there's a follow through. Du equals 2x dx. I'm going to solve that for dx all by itself. And then I'm going to come over here and just sort of recreate this integral now. I didn't really do anything about that x up there in the numerator, but I'm going to decide to let the entire denominator be u. And in place of dx, of course, I've got that swap, du over 2x. So this is great in the sense that the x up there in the numerator that I ignored is totally gone. And I have left here the integral of 1 over u du, which I now know that integration rule, that's our log rule, that's natural log, absolute value of u plus c. And I forgot the 1/2, so let me go ahead and put that 1/2 in there. Oops. So maybe I should circle it. So here's our antiderivative, which of course is not finalized because, you know, it has to be in terms of x. So we'll go ahead and swap that in. And you can always use absolute value symbols on the natural log. In this case, you don't necessarily have to because no matter what you put in for x, it's always going to be positive. So either of these would be totally acceptable. So you can relax the absolute value in this case because the inside is non-negative. All right. Moving on to problem number 2, this is also a basic U substitution. If you look at it, it's a little bit clunkier than the last one. That whole denominator is in the power of 2. So I'm going to get started in exactly the same way. It's the exact same, basic U substitution. We're going to let U equal that x squared plus 4, and that fits more in line with what we normally do for a U substitution. Something sitting inside another function. So of course I have the same exact supporting work here. Everything is incredibly similar. Where it starts to get a little bit different is when I look at what I have when it's left over. So I'm just trying to push an issue here. Over here in the denominator is where I have u squared. Okay, so it looks a little bit different. It's not just a u, it's u squared. I am also going to replace the dx with du over 2x. And I'm just pushing an issue here on basic integration strategies. Of course, you see the x cancel with what I had in the numerator from that kind of dx substitution, which is great. I'm going to remember the 1/2 this time. So this would be, I'm going to take that 1/2 out. And what I want to realize here is that you have 1 over u squared du. Please make sure that this is my just way of pushing the issue here. This is a power rule integral. So I'm going to write it like that. It's u to the negative 2. Don't use a log here. This is not a log rule. You only use a log rule when it's 1 over u du. So I'm going to use the power rule. I'm going to add 1 to the exponent, divide by my new exponent, add that integration, that plus c, that constant of integration, and of course not forgetting the 1/2. Okay, so just my way of pushing the issue here that 1 over u du involves a natural log, but any other power down there, that's a power rule. So I'm going to rewrite this so that it looks a little bit nicer. It's a negative expression. This is just being multiplied. So negative, let's say 1, and then that u to the negative 1 comes down. So I always just want to remind you of your basic skills. Even when you move on to Calc 3, this is all like really important stuff that you can diagnose and understand the differences between these integrals for 1 and 2. Okay, let's move on to problem 3, which you can see here that, I've got this 1 over x squared plus 4. And that is not going to work with the u substitution, because you can see from before I'd have this dx substitution that is not going to check out for me. But if you look at it, I'm gonna recognize an arctan situation here. I'm gonna recognize that, like, well, if I let u equal x, that's gonna be u squared. If I let a equal 2, then the 4 is really 2 squared. And of course, I'm recognizing this as arctan, but there's still a follow through there for the dx. So I'm going to translate this whole guy over. So once I've just done that, right, like this now transforms, what do I now have? Well, I still have this 1 over. And remember, I'm the one that said, I'm going to let u equal x, so that means this is u squared. And I'm going to let 4 equal a squared. And in place of dx, I have du. This is exactly the derivative for arctan. So I'm going to go with that antiderivative. So I'll come down here and I'll say, well, that's really just 1 over a arctan of u over a. I'm going to put the puzzle pieces back in here as far as making sure that I've got everything together. So my antiderivative will be 1/2 arctan of x divided by 2 plus c. Okay, so you've learned a lot of stuff in this class, and it's all sort of coming together here, and you've got to diagnose these issues as they move through. Okay, so I'm going to try a couple of things here on problem number 4. I'm going to see where this gets me here. I don't see any kind of inverse trig going on here. I think what I'm going to do is fall back to the first, real method that we learned, which is u substitution. I'm going to let the u be the entire denominator. I'm going to see if that's going to work for me. And I'm going to go through the motions and do the follow through. So there's my derivative, slap a dx on it. And then I'll just solve it out for dx, right? I'm just going to divide through by 2x plus 2, and let's see how this transforms. I've got x minus 1 up there that I kind of ignored for the most part, right? I let the whole denominator be u, and in place of dx, I'm replacing that with du over 2x plus 2, which I have some hope, right? Like maybe I could just finagle that little substitution part there. Let's just rewrite that 2x plus 2 as 2 times x plus 1. Well, unfortunately, that does not work. I can't cancel. Let's see if I can highlight here. I can't cancel this x minus 1 with this x plus 1. They are not the same thing, and it doesn't mean that you did anything wrong or horrible or, off the mark. It just means it didn't work, so no big deal. We'll just put a line through it. Okay, sometimes a u substitution doesn't work. That does not mean that this process is worthless. It's actually really good. It just means try something else. So that's kind of how chapter 8 goes. Like, all right, I tried that. It didn't work. What else do I see? What else can I do? So what I will do is take a look at that integral and see what else can I find about it. How else can I represent this? Well, one idea would be, let me just take a look at that denominator and see if I can factor it. And let's see, minus 3 plus 2. So plus 3 minus 1. That denominator factors, that's an old Algebra 1 trick that you're employing. What can I do with these expressions? Is there any algebra I can work on? And right here you can say, well, look, can I cancel the x minus 1s? Of course you can. They're exactly the same. Our problem here is gone, right? I had a different sign in the middle. This is absolutely perfect. So I will cut these out. These are gone. And what I have left in this whole process, right, is I have the integral of 1 over x plus 3 dx. Now, technically, that's a little u substitution, right? You're going to let me slide this up here. You're going to let u equal x plus 3 and du equals dx, and really you're using that log rule again. So natural log, absolute value of u plus c and you are out of this problem. So sometimes you have to be a little bit crafty, and sometimes the method that you choose depends on what's in front of you. Sometimes your kind of flow chart, if you think about it, of what should I try next, it sort of gets altered by what's in front of you. All right, so these are things that you know how to do at the moment, right? Kind of working in all of our old skills. When it comes to the last two down here, you cannot do these right now. There is no way for us to handle either of these two issues. And what I want to recognize here is this first guy down here. U substitution totally fails. That's not going to work. U substitution fails. It doesn't have anything crafty like example 4, where I can cancel out a factor and make it prettier. It only has a 1 in the numerator, so I can't use my cute algebra skills that I relied on. And when I take a look at this guy, this is not awesome either, because there's a minus sign in there. I was able to handle this very well on example 3 when it was x squared plus 4, because I was able to kind of push that arctan look to it. The 9 doesn't bother me because that's just a coefficient, you can take it out. But this is not U substitution, and it's also, this is not arctan. You see that minus sign, and we've got a problem. So U substitution doesn't work. Kind of morphing it to a fancy derivative rule doesn't work. So I'm going to move into what I could do when things would factor. Do you see how both of those denominators are factorable? Let's kind of focus on that for a second. This can factor. We did that in example 4. And I think quickly with your head, you can see that this can factor. It can factor into x minus 2, x plus 2. So I guess that's what I want to kind of move toward. Like, how would you know to try a partial fraction decomposition? Before we even know what that is, by the way, it's an integral that you've tried other methods on. They don't work, but you happen to notice that denominator can break down algebraically. So that's sort of our trick here and our technique. So I'm going to write that out because I think that's an important thing to discuss. So I'm going to write out partial fraction decomposition to me. This is a advanced algebra skill that we are revisiting for a particular means. So I'm going to describe this. This absolutely is an algebraic technique. You may have learned this in a previous algebra class. You may not have. I don't remember learning it in Algebra 2, but I do remember learning it in pre-calculus. That was a while ago. But an algebraic technique, what we're going to try to do is we're going to try to rewrite the integrand. Because that's our goal. We're trying to integrate something. We want to try to transform the integrand, legally, of course, using good algebra skills. And we want to transform that integrand into smaller components. Let's not have something that looks so large and overwhelming. Let me spell correctly. Components. I'm talking too much. Okay, there we go. All right, so most of your math life has been spent doing something like taking this expression and getting a common denominator. Your teacher would say, hey, simplify that, which is code for get a common denominator, and put it all together as one giant fraction. That is how most of your math life has gone. And as always in calculus, what we tend to do is deconstruct those ideas. What I am going to have instead, let me just undo all those things I just did. What I am going to have instead is in front of me, I'm going to be charged with integrating this cohesive left-hand side. And I don't know how to do that. I can't cancel any common factors. I see that the denominator is factored, which is great. But what I would like to do, what I would rather do, is I would like to deconstruct this. I would like to go backwards from my Algebra 1 and Algebra 2 skills. And instead of having this cute one colossal fraction, I want to break it down into smaller pieces. I actually would prefer if I could just have an equal statement of these individual pieces, because let's be honest, That means you can integrate term by term. When they are separated by a plus or a minus like this as separate fractions, these are two smaller separate integrals and very doable, right? So if I just kind of keep working on this just for the sake of it, this is the whole point. I can integrate this in my sleep, right? This is the same thing as like whatever, just like some kind of coefficient, which we don't care about, 1, 2, -5, doesn't matter, over x plus 5. My antiderivative here would be, well, whatever that coefficient is, times the natural log of the absolute value of x plus 5. And then your other fraction here, integrating that, well, no surprise there. It would just be your coefficient b that you're kind of removing outside the integral, and it would be natural log absolute value of x plus 1. So this would be great. This is what's going on here. You are going to be given this integral to work on. You are going to rewrite it into this smaller form so that you can actually come up with an evaluation for that integral piece by piece. That's the whole point of partial fraction decomposition. It's very algebraic. You learned it in a previous math class. Even if you didn't, it's highly algebraic. There is no calculus I'm going to discuss, but I'm going to show you how do you take an expression like this and magically know what those coefficients A and B are. We're going to solve for them very efficiently. And most people really like this. I think coming off of trig substitution, let me just tell you, this is a lot more friendly. Most people do not enjoy trig. They do enjoy algebra, and maybe coming off of trig substitution, this just feels a little bit more refreshing. So anyway, that's the whole point of what we're going to be doing. Now, what I'd like to do is discuss very briefly, to end this video, what our setups look like. And I might come back to this at the end, I'm not sure. But let me sort of get rid of all of this stuff that I had, just so I cannot maybe junk up my picture totally, right? Let's just cut that out. Okay. I want to talk about obviously there are 4 different scenarios going on here of what your template kind of looks like. What could you have been handed? Well, you could have been handed distinct linear factors. That means different linear factors in the denominator. I'm totally ignoring the numerator, by the way. Okay, I'll get back to that in a minute. But I have different linear factors, and so when you do that, you are going to break it down into, well, there are 2 factors. So you're going to have 2 fractions, and I don't know what that numerator, that coefficient is. I'm just going to call it A, call it B. It doesn't matter if you put the B here and the A here. They're just placeholders. They're just variables. It doesn't matter. So this is how you would set it up. And we'll talk about going through the process of evaluating it. Okay. What I want to talk about is this next one. This happens a great deal, and put a star next to this to make sure that you stay up on that. This is one that a lot of people miss. Forgot I wasn't on a pencil. There we go. So this is repeated linear factors. So what I can see here is that I have a factor of x minus 1 that occurs twice, right? Sometimes it might actually be written twice. And sometimes that's helpful and sometimes it's not. I actually like to see the power on it. But you have a linear factor that's happening more than once. Notice how interesting this setup is that, notice I have c over the x plus 5. That's a different one. But that x minus 1 squared, I need one fraction with x minus 1 to the first, let's say, and then I need another fraction with a coefficient on top with x minus 1 to the second. Okay, and had there been x minus 1 cubed, you'd need another fraction with a coefficient on top and an x minus 1 cubed. You basically need to represent every single power of that repeated linear factor. So you're going to see that show up in some of these example problems. Okay. Now, the other one you will see is distinct quadratic factors. Again, think about distinct as different. And I'm going to add something in here. I'm going to add an extra word, so bear with me. I'm going to cancel out my little extra there. And I'm going to add a word here. I am going to add the word irreducible. Distinct, irreducible quadratic factors. That means they're different, right? Distinct means different. And irreducible means, something that can't be broken down further. So let me clarify. Let me go back up a smidge. This is a quadratic factor, but that is a reducible quadratic factor that breaks down into two distinct linear factors because you can actually factor that denominator. So that is not what we're talking about in this third bullet here. Okay, this, while it looks quadratic, take a look and make sure, like, hey, can I factor it? Oh, I can? This would be the first case. This is distinct linear factors. What we're talking about in this third bullet is distinct irreducible quadratic factors, which means, look, that does not factor any further. Neither does this one. You can't do anything to break these down into two linear factors. So it's okay. There's a lot of quadratic expressions that don't factor. That's why you learn things like completing the square and quadratic formula way back when you were in Algebra 1. But it's okay. They don't break down, no problem. Notice how quirky this setup is, right, in terms of what's happening. Get those out. I'm going to write every single of those irreducible quadratic factors, and I put a linear expression on the top. Ax plus b, that's a linear expression. I have a quadratic denominator, irreducible, and I have a linear numerator. Same thing here, irreducible quadratic denominator, and I have a linear numerator. Now, it's very possible that like d could be 0, right? It's totally fine. Whatever happens, happens. Again, I'm going to show you how to find these coefficients. You are not going to be guessing and checking. Maybe a is 1, maybe a is 7, maybe it's 1/4. You're going to have an algebraic skill of how to know for sure what these coefficients are, and it's pretty efficient. Okay, the last case I think is a little overboard. You will not see me ask you about, but I want to show you the idea about this last one. Again, I'm going to add this extra term in here. Repeated irreducible quadratic factors. And let me just give you an example. Let's say you have 1 over x. Actually, let me do this. Yeah. Okay, I'm going to do it. I'm going to do 1 over x squared. Let's talk about it. Sometimes I have ideas when I'm talking. Here we go. So this is what I'm really talking about here. This is your irreducible quadratic factor, and it's happening more than once, right? What I decided to throw in here is a linear factor, a repeated linear factor happening more than once, right? What would my setup look like? Well, here's how I write it out. It's just a way for me to hammer this home. On the the repeated linear factor, I'm going to set it up with a over x to the first and b over x to the second. You represent every single power of that factor. Had it been x cubed, you know what? Let's just do it. Let's say it was a cubed. What would I do? I'd have c over x cubed. That's how you handle a repeated linear factor. You're definitely going to see us do that in the example problems. Now here I have a repeated quadratic factor. Well, what do? I have to put a linear term in the numerator, and I have to put that irreducible quadratic factor to the first, and then, what letter comes next? I have to have another, A, B, C, D, E, F, G. I have to have another linear numerator for this quadratic factor that happens twice. So that is chaotic, right? That is highly ridiculous. But that's how the process of these setups go. And what I want you to kind of focus on here, why are the numerators the way that they are? The degree of the numerator is always one less than that guy you have here. If you had this repeated linear term, then all your numerators are degree 0. They're all going to be sort of this idea of having a coefficient up here. But anytime you have an irreducible quadratic, well, its numerator is going to be linear. If you happen to have an irreducible cubic, well, then its numerator would be quadratic. So obviously there's a certain time and place where computers sort of run the show, and anything beyond this would require a computer. All right, so we will get into the next video of how to actually do this. What is the algebraic technique that's going to do it for us, and we'll evaluate those last two integrals.